That's the end of our look at the different mathematical expressions that we'll use to describe signals. What we want to look at now is how we can take those mathematical descriptions and modify them to perform certain operations on our signals. And again, the kind of operations we'll be interested in are amplitude transformations, time transformations, integration and differentiation, and averaging. In terms of amplitude operations, there's two or three that we're particularly interested in. The most common that you've already encountered numerous times is amplitude scaling. Here, whatever our signal is, x of t, if we want an amplitude scaled version, we would simply multiply x of t by a scalar multiplier value c, which would change and scale the height of the signal at every point of time. So if, for example, c was a fractional value, and we had a function that had a maximum value of a, after we multiplied that function by c, its new maximum would be c times a. If c happens to be a fractional value, it would make a smaller function. It would scale down or attenuate the signal. If c is a value that's greater than 1, then we would be actually multiplying, expanding, or amplifying our signal, meaning we're scaling it in the vertical direction by some common factor. To take a real-world example, if we take a causal exponential signal, x of t equals 4 e to the minus 3t u of t, and drew that on a graph, if I want an amplitude scaled version of that, for example, when scaled by a factor of 5, 5x of t would be simply 20 e to the minus 3t u of t, a function that's 5 times larger in the vertical direction than the previous example. Amplitude shifting or offsetting means we're going to add a constant value to every point on a waveform. So add a k plus x of t. And we know graphically what that will do is take the whole waveform and shift it upward or down, depending on if k is positive, it'll shift it up. If k is negative, it'll shift it down. Notice that amplitude shifting is something that can take a signal that was once causal and make it non-causal, because now all those values that we needed to be 0 for negative time suddenly have a fixed value that's non-zero. We'll find out later that this kind of offsetting also, if it's dealing with the response of a system, and we see an offset like this, that would imply a system that's not entirely linear. And so we're not going to encounter a lot of amplitude shifts, at least not intentional ones, in our analyses. The other operation that can happen in amplitude is an offshoot of scaling, and that's inversion. So if we go back to our scaled look, if the multiplier c has a negative value, then not only will we scale the height of the waveform, but we'll actually flip it over the y equals 0 axis. And that would be what we would recognize as signal inversion. In terms of time, we've already looked at how we can shift certain functions in time. We looked at that with delta functions and rectangle functions. So let's generalize our approach here. If I have a signal x of t that has a particular shape, and I want to create a time-shifted version of that, we'll call it y of t equals x of t minus tau. First thing we need to be clear about is, if I have an argument t minus tau, which direction am I shifting the waveform in? There's several different ways to remember this. One way is to simply recognize that if we have a t minus tau and negative tau, minus implies a delay. And by delay, we need to shift the waveform over to the right, meaning it happens later. It starts later. So a delay, a negative tau, would imply shifting to the right. Time advance, meaning that something happens sooner, would be a t plus tau. Now, if that reasoning escapes you, the other way we can approach this is to look at what happens and where we get the x of 0 value in our new function once we time shift it. So ask the question, at what time t in our new function y of t, that's a time shifted version of x, should we see the amplitude value that's occurring at x of time t equals 0 back in the original waveform? So if y of t is x of t minus tau, and we want to know when is x of t minus tau equal to the value of x of 0, then t minus tau must be 0. And solving for t, that will only occur at time t equals tau. So y of the time tau is going to give us the value of x that happened at x at time 0. So if we have again an x of t minus tau, that's going to imply a shift to the right for tau being a greater than 0 value. If we have a time advance, that would be a value of tau less than 0. So we have an x of t minus minus, or positive value. For example, x of t plus 1, that implies a shift to the left so that things start sooner. Now, how does that show up in our mathematical expressions for our different waveforms? Let's look at our exponential example. X of t is 4e to the minus 3t u of t. If I want to create a time-shifted version of that waveform, I simply replace all the time arguments t with a time-shifted argument t minus 2. But notice that it happens to happen everywhere. It has to happen in the exponent of the e to the minus 3t, has to become e to the minus 3 times quantity t minus 2. And the t in the unit step also has to have a u of t minus 2 so that it also shifts over with the exponential waveform. Here's one to try yourself in your notes. Here I have a single sawtooth that starts at t equals 0 and goes to t equals 1, and we'll call that x of t. Now I'd like to know and have you draw what would x of t minus 1. So if we have a shift of 1 in that, how would that appear? Please draw that in your notes. And if you've done that, hopefully you end up with something that looks like a shift like this, where again, x of t minus 1 implies a time delay by 1 second. So the starting point at t equals 0 shifts over to t equals 1. The end point at t equals 1 shifts over to t equals 2 seconds. Time advancing, on the other hand, if we put back our x of t back starting at t equals 0, the waveform x of t plus 1 implies it's shifted to the left by 1 second so that it starts sooner than the previous. That would be a time advance. The second operation we can do in the time direction is scale the time direction of a function. And that means we're going to be expanding or shrinking along the time axis. Think of a cosine or sine signal when you change the frequency. It spreads out or gets narrower. Similarly, we want to do that sort of time scaling in a standardized way in all of our functions, like rectangles and unit steps and others. So if I have a function x of t that we know its shape, and I want to create a time-scaled version of that, I would multiply the time argument by some scalar value, for example, shown here as alpha. So now we have to ask the question, if x of t is as shown, and y of t is a new function that's a time-scaled version of that, x of alpha times t, is that a compressed or an expanded version of the waveform x of t? One thing we can notice is that in our new function y of t, the time argument is progressing alpha times faster for our y of t than it was in the x of t function. So if time is happening faster, we're making more progress for less progression along the t equals t axis, the time axis. That makes it sound like we're going to be compressing the waveform. We're going to be squeezing it in. The other way we can think about that is look at the endpoints of our signal. Back in the original signal x of t, in our old time axis, goes to 0 at time t equals 2 seconds. In our new y of t, where things are moved along by alpha times t, the endpoint should happen earlier at t new equals t old over alpha, or in this case 2 over alpha. So as shown here, if alpha is a positive value greater than 1, x of alpha t is going to be a time-compressed version of x of t. It's going to be compressed inward. Notice it's compressed from both directions, from the positive t and the negative t directions in towards the origin at t equals 0. So both endpoints will move in proportionally, and what used to be at -2 and +2 now is at the numeric values -2 over alpha to +2 over alpha. An example of a time-compressed signal would be the expression y of t equals x of 3t. Now, if my value of alpha is a fractional positive value, like 1/4, that implies that we're going to expand the function along the time axis, or time expansion. So for example, y of t equals x of t over 4 would be taking the x of t function and spreading it out by a factor of 4. Notice we don't change the amplitude of the signal when we do time compression or expansion. How about our exponential example signals? Shown here on the left is our x of t equals 4 e to the minus 3t u of t. Let's perform a time compression. Let's look at what is x of 3t, where so alpha is a positive value and it's greater than 1, it's 3. This will be a time compressed version, which means it should look like a skinnier version of our exponential, causal exponential on the right. Mathematically, if we take our original exponential function and replace all the time arguments with 3 times t, we have 4 e to the minus 3 times 3t, u of 3t. What does that look like? Well, we can multiply our exponents together and see that it's a 4 e to the minus 9t, which is an exponential that decays 3 times faster than the original e to the minus 3t. What about the u of t? What's shown here in these expressions implies that u of t is the same as u of 3t. Well, think about that. If we draw a unit step function that's 0 for all time less than 0, 1 for all time greater than 0, and I expand or compress that signal along the time dimension, I'm not going to change the shape of it. It's going to look identical as long as it was not a time-shifted unit step, as long as it makes its transition from 0 to 1 at t equals 0. So our u of 3t is equivalent to u of t, so I can just drop that extra 3t. Let's look at an example of time expansion. If I choose a magnitude of alpha that's a fractional value between 0 and 1, for example, if we choose alpha equals 1/3, so our y of t is now x of t over 3. If x of t is our exponential shown on the left, 4 e to the minus 3t u of t, and I do a time expansion by a factor of 3, again we'll replace all the time arguments t in the original function with t divided by 3, and simplify and find that our exponential now is no longer e to the minus 3t, but now is e to the minus 1t, an exponential that decays 1/3 as fast as the original function. Once again, a expanded version, u of t over 3, I would argue, is the same appearance as u of t itself, and so we can just drop that extra expansion factor. If we happen to have a waveform like this that's not written out explicitly mathematically, or that's written out in kind of a piecewise fashion, where we say this function has a certain form, like x of t equals t minus 1, but only over a certain interval, 1 less than t less than 2. If I'm going to do a time scaling on this kind of function, again I have to replace the time arguments with the new compressed arguments, both in the equation that defines the signal and also in the relationships that define the endpoints over which that particular function applies. So x of 2t equals 2t minus 1 over the interval 1 is less than 2t, which is less than 2. Simplifying that range now to be in terms of just time, we'll divide everything by 2 and say that x of 2t equals 2t minus 1 for the values of t that are between 1/2 and positive 1. We see the illustration of this in the picture above, that x of t, notice comparing x of t to x of 2t, we've compressed it around back towards the t equals 0 axis. So the 1 is compressed back by a factor of 2 to 1/2. The endpoint at 2 is compressed back to 1. Time reversal is a special case of time compression or expansion where our alpha has a negative value. In the case of time reversal, it works the same way, except we're not changing the width, but what we're doing is changing the direction of a signal. We do that by replacing all time arguments in our analytical mathematical function describing signal with minus t instead of t. Graphically, if we had a signal like the one shown here on the left, x of t, with whatever shape it has, if we want to create the time reversed version of that, the signal would have the same basic shape, except it would be flipped around the t equals 0 vertical axis. So it would be as if we were running the signal backwards in time. So what was previously in the positive t direction now is in the negative t direction, and vice versa. How we show this analytically again, if we have a mathematical expression describing our signal, like the one shown in the example here, x of t equals 4 e to the minus 3t u of t. To create the time reversed version, we would replace all of the time arguments in that expression with minus t. So the minus 3t in the exponent of the exponential becomes minus 3 times minus t, or plus 3t, and the u of t's time argument also becomes u of minus t. Now what do these changes do to the shape and appearance of our waveform? Well, we know 4e to the minus 3t is an exponential waveform that decreases with positive time. The case of a e to the plus 3t, though, would be one that's increasing in time as we go to the right. U of minus t is a unit step that's also time reversed, so it would be 1 in the negative t direction instead of the positive t direction. Seeing those things graphically, on the left we have our 4 e to the minus 3t u of t original signal. Its time reversed version would be 4 e to the plus 3t times u of minus t. That u of minus t is a time reversed step function, and 4e to the plus 3 is an increasing exponential. When we multiply those together, we would have the waveform that looks like the mirror image of the original signal that we had when we started, the 4e to the minus 3t. Here's another simple example. Here we have a triangle that goes in the positive t direction between 0 and 1. If we created the time reversed version of that, it would be a backward facing triangle going in the negative t direction that ends at minus 1. Those are pretty straightforward concepts now. It becomes a little more challenging if we're doing combinations of time operations, particularly time shifts with time reversals and or time shifts with time scaling. It turns out these combinations are things that we're going to do quite often, particularly when we get to time domain analysis with convolution. It'll be very common that we have to flip and shift a waveform, and doing that properly is going to be critical to our application of convolution. So here we want to get some practice with what is the right way to do combinations of time operations, in particularly time shifting and time reversal. For example, if we had some signal x of t and we wanted to create a new version of the signal we'll call y of t, that's a time reversed version, so it's like x of minus t, but in addition has a time shift of plus k, so it would be x of minus t plus k, or rearranging the arguments if you prefer, x of k minus t. The minus t implies time reversal, the plus k implies a time shift. If k is itself a positive value, that implies a shift to the left of the waveform. Now, question is, which operation do we do first? Do we do the time shift followed by the time reversal, or the time reversal followed by the time shift? The easiest and most straightforward way to remember to do this is to first do the time shifting that's implied. So here, if our k was 2, was a positive 2, implying a time shift to the left by 2 spaces, we would first apply that to our x of t waveform. So if in the example shown here, x of t begins at a time value of beta and ends at a time value of alpha, if we do a time shifted version of that, shifted to the left, it would be, the starting point would now be at b minus the time shift, b minus k, and the other side would be at alpha minus k. We do the shift first, and then we flip that shifted version around the t equals 0 axis, so perform the time reversal second. That then moves what the edge that was formerly at beta is now flipped around to the other side at negative beta plus k, and the right side of the signal that formerly was at alpha now is at minus alpha plus k. This would be a proper execution of the combination of time shifting and time reversal, first doing the shift, then doing the reversal. If we were faced with a combination of a time shift with a time scaling, this would be also the proper order of operations. We would perform the time shift first, then rescale the shifted waveform. If we're just doing shifting and reversal, we do have one other option for how to do this. We could, in fact, perform the time reversal first on the waveform. So that would bring our signal back around looking like this. And then we could perform the time shift secondly, but we have to take into account the fact that we've already reversed the signal and then shift the time reversed version in what seems like the wrong direction. So if our time shift argument was plus k, where k was a positive value, usually implying a shift to the left, if we're performing that shift after we do the reversal, we'd have to, in fact, shift it to the right, what we would consider the wrong way. So if we do the reversal first, it affects the nature of the secondary shift operation. That's why I would suggest it's actually easier to remember to do the time shift first and then either the reversal or the compression operation. That's the safest way and the more straightforward way to do it. Here we can see how to run a test for if you ended up in the right position. We can compare single values in each waveform to see if they showed up in the right space by plugging in the appropriate time arguments. Here's another chance to try out these concepts. Here we have a signal that's a tu of t minus tu of t minus 1, so a ramp function that's truncated. Now if you needed to take that x of t waveform and draw a flipped and shifted version of it, x of minus t minus 1, try to draw that into your notes now. We'll pause a second while you do that. And then let's compare your answer to the correct answer. We would do the time shifting first, which would move that triangle over to the right by 1's position, and then flip around the t equals 0 axis, which would bring its leading edge, which was at 1, over to minus 1, and its trailing edge that was at 2 now flips around to minus 2. Now some more advanced operations on signals that you're familiar with from calculus: integration and differentiation. Integration, although we don't always recognize this, is actually a kind of smoothing operation. It takes things that have sharp edges and making those edges less drastic. For example, here shown here is a time integral, the integral from minus infinity to t of x of t. Now, again, this is not a definite integral, meaning there's not a single numeric answer for this. The result of this integration is a function of time, that upper limit of integration being t, meaning when we evaluate the integral, we'll have a function of t when we're done. Here in the picture, we see two different functions, x of t and y of t, where x of t is actually the time integral of x of t. So for any time value t in the y of t graph, the amplitude of the point at that position is equal to the integral of everything that happened in the x of t function up into that same instant in time for x of t. So for example, for t equals 0, y of t has a value of 0. And if we look over the x of t function, the integral from minus infinity to t equals 0 of that x of t function is also 0. Moving over to, for example, t equals 1, in y of t we have a value of 1/2. For 1/2 represents the integral of x of t from minus infinity up to time t equals 1, which is the area under that little rectangle of 1 by 1/2, or 1/2 for total area. And so if you look through the rest of that, hopefully you can convince yourself that indeed y of t does represent the area under x of t as we accumulate our way across the time axis. Notice that while x of t has vertical discontinuities, y of t doesn't, has just some slopes. And if we were to integrate y of t again, we would get even smoother transitions. So integration is by nature something that smooths out fast and sharp things. The way we can create an integrator electronically is this simple circuit, is an op-amp circuit where if we put a capacitor in the feedback loop, that capacitor gives us the integrating nature that we need to create an electronic integrator. Weighted integration is a modification to basic integration where the function that we're integrating, x of t, is weighted by another function, h of t, before it's integrated. Now a weighting function like h of t is just a mathematical device that's could be used for summations, could be used for integrals, could be used for averages. And the idea is we're trying to modify x of t so that the result of the integration or the result of the averaging isn't equally weighted by all of the elements of x of t. It's like a way of giving more emphasis or more influence to part of the waveform and de-emphasizing other parts of the waveform. So h of t has some shape, tends to be one that tapers off at the edges so that further away points have less influence, and that gives us a way to give more weight, more emphasis, more influence to part of the waveform than others. The way we would implement that electronically is through this sort of circuit, using not a pure integration with simply a capacitor feedback in the op-amp circuit, but by putting a resistor in parallel with that, we create what's called a linky integrator, one that has, in this case, an exponential weighting factor. Now, exponentials are not the only kind of weighting factor that we could use. This is just one example. Averaging is just as you might consider. If we wanted to know the average value of a function, we would generally use a time integral to find the average. And usually it's not the average over all time, where we would look at the average over some finite length of time. To find that finite width average, we would integrate our original function over the time span that we're interested in and divide it by that time span. Now again, if we wanted to give more weight or more emphasis to some parts of the waveform, for example, in a window averaging, you might want to give more weight to the center value of the window you're looking at and less to the peripheral values. So we might multiply our original function by a weighting function, one that emphasizes some parts and de-emphasizes other, before we do the averaging integration. So here, for example, is the idea of using a moving average. The fast and jaggedy line A is some original data that was collected. That could be temperature data, it could be, who knows, from some source. It's a little bit noisy, a little bit jaggedy, and by using different windowing techniques, we can average some number of these values and come up with their windowed average value. And by controlling the length of the window, we can control how much smoothing we get to the data. And by using different weighting functions, we can change the nature of that smoothing somewhat. So in this case, we have lines B and line C that are much smoother, much slower changing. These represent window averages of that original signal. So it's like we define some width of time that's our time window, and we move that window along in time and take the average of all the values that fall within that window in time, and that average represents, we compute that at every position and assign that value to each position of our average signal, and then move that along, carrying out that integration at all points and giving us eventually that time averaged window function. Notice in the one here shown by creating a uniform windowed average, we end up with a much smoother function. It's not as jaggedy, not as quickly changing as our original data, but also gives us kind of the trend of the data without all the noise. Differentiation, you're probably even more familiar with than integration. Differentiation is something that actually emphasizes changes in things. And if you have a waveform that has a little bit of noise in it and you differentiate it, for example, it looks even noisier. Conceptually, we can consider the derivative of a signal to be analogous to the slope of the signal at each point, and being the limit of the change in x with a change in time at every position as we let the width of the time that we're considering go to 0. A familiar place where differentiation is used in signal processing is actually in the retrieval of data from magnetic and optical recording devices. There we might have these places where we have to look at how data is stored on a magnetic disk or an optical disk. In this case, in an optical disk, it might be stored as light and dark regions, and where what's important to us is where are the edges of those regions. So on top might be the reflectance signal off an optical disk as it goes over a light and dark spot, and what we want to know is what are the positions of those edges. Particularly by taking the derivatives, we can highlight where are these edges happening, and we can tell by whether the derivatives go positive or negative on whether our edges are going up or down. So signal differentiation is an operation that's often performed in data storage. These are just a few examples of the basic operations that we can perform on signals. Again, ones we want you to be practicing with in homework are particularly the amplitude and the time operations, time shifting, time scaling, time reversal, combinations of those, along with perhaps amplitude scaling and amplitude shifting, and also getting comfortable with using the different mathematical descriptions for different signals. So please try the homework problems, and we'll be back to look at special kinds of signals, other signal measurements, other kinds of signal averages, signal power, and we'll be back to look at some more advanced operations on signals